All right, Chemistry 1401, Practice Exam 2. This is part 2. Of course, you can find part 1 on my YouTube channel. And let's get started with question 16. It says, which of the following molecular classes may have a linear shape? For this and all subsequent questions that are similar, we use the letter A to represent our central atom, X represents surrounding atoms, and E represents the number of lone pairs on the central atom. Now remember that when we're dealing with regions of electron density, our reds, this concerns single bonds, double bonds, triple bonds, lone pairs, and even unpaired electrons. And so when we have a surrounding atom or a lone pair, right, these are both going to represent regions of electron density. And so for the first formula, I have AX2, E2, and thus it has 4 regions of electron density. And so my electron geometry is going to be tetra that our 2 X's, I'll draw them in the plane. I don't know why I'm drawing them with lone pairs. I don't really have to do that. Lone pairs, making it more complicated than I need to. And we'll put an electron, a lone pair down here, and we'll put a lone pair like this. And so the molecular geometry of this molecule would be bent. So neither of those are linear. Let's take a look at the next one. We have AX2E3. Here we have 5 regions of electron density. So the electron geometry will be trigonal bipyramidal. Okay, and we could draw that molecule out. We'll say, okay, well, we're going to have A, we're going to get our 2 X's as far away from each other as possible. And then we'll have 3 E's in the equatorial positions like this. Okay, and so you can clearly see here that the molecular geometry is in fact, the molecular geometry is in fact linear. Okay, and the question is, which of the following molecular classes can have a linear shape? And so the answer is this one here. Let's take a look at the next ones just to be thorough. We have AX4E2. That's a total of 6 regions of electron density. And so that's going to be octahedral. And if we draw that out, we would have A with 4 X's. I'll put them like this. Okay, like that. And then we're going to have our 2, lone pairs down like this. And so the molecular geometry would be square planar. Let me see if I can move this guy out of the way. We're in the space already. Let's see if I can move it up here. There we go. Good enough. What's next? We have AX2E, so that's 3 regions of electron density. And so our electron geometry will be trigonal planar, right? That would look something like this, where I have my A, I have 2 X's like this, and my E, and then you can see that the molecular geometry is in fact bent. And then finally, for the last one, we have AX3. The electron geometry and the molecular geometry, since there's no lone pairs, are both going to be trigonal planar and trigonal planar. And that would look something like this, where I have my A with 3 X's surrounding it, like that. Here we go. Number 17, which of the following molecular classes may have a bent shape? I'm going to go through this one a little bit quicker. We're looking for something with a bent shape. If we start with AX3, of course, that's going to be trigonal planar in terms of both its molecular geometry and its electron geometry. If we have AX2E2, that's 4 regions of electron density. We're going to have 2 X's like this. We'll have a lone pair like this because, and then a lone pair here because our electron geometry is tetrahedral, but our molecular geometry is in fact bent. And so this is the correct answer. Let's again look at the rest of them to be thorough. We have AX2E3. So I'm going to have my A, and I'm going to have my 2 X's like this because it's going to adopt a trigonal bipyramidal electron geometry. But of course, it has a linear molecular geometry. The next one is AX3E. This one is going to have a tetrahedral electron geometry because it has 4 regions of electron density. So we'll put in, why don't we put the lone pair up here Put X down here, another X in the back. And so, again, the electron geometry for this one, the one I've written in black, is tetrahedral, but the molecular geometry is trigonal pyramidal. And then the last one, AX2, these two are going to get as far away from each other as possible. So we'll have A with an X here and an X here like this. And so both the molecular and the electron geometry, because we have two regions of electron density, this will be linear. So to summarize, the first one, the molecular geometry is trigonal planar. Okay, this one here is bent. That's the correct answer. This one here is linear. The next one is trigonal pyramidal. And the last one is also linear, like that. Okay, first two questions complete, almost done, right? Okay, let's take a look at question number 18, which just asks us more about electron geometry. It says, what's the shape of a sulfate anion? Wow, this is one of those questions that reminds me of an ACS final type question, because there's kind of two questions in one here, isn't there? You know, it's asking you for molecular geometry. That's what it means by the shape. But it also tells us a sulfate anion. And so you have to know what a sulfate anion is, right? You have to know that it's SO4 2-. That's what a sulfate is. So how many total valence electrons do we have in sulfate? Well, we have 6 from sulfur, and then we have 4 oxygens. Each one of them has 6. That's 24 plus 6. That gives us 30. And then we add, oops, I meant to add 2 more for the negative charge here, the 2 negative charge. And that gives us a total of 32 valence electrons. And let me double check my math here. I got 24 plus 30, 32. Yeah, looks good. Okay. Well, our sulfur is the least electronegative element here, so it's going to be our central atom. Now, if we, start drawing, bonds to our oxygens like this, okay? Well, what do we know about oxygen? Oxygen usually has 2 bonds in 2 lone pairs. And if I start, if I was to just draw this Lewis structure like this, okay, I would have a -1 charge on all of the oxygens like this. And then to figure out the formal charge on the sulfur, I'll just do it out loud without writing it down. Sulfur has 6 valence electrons. Subtract 4 sticks and no dots gives us a charge of +2. Okay. Now, when you add up -4 and +2, you do get 2-. And so this is an okay Lewis structure, but you might remember that we tried to minimize formal charges in a Lewis structure. And there is a way that we could minimize some of these formal charges, okay? We could take one of the lone pairs on an oxygen and we could move it over here. And then we could take a second lone pair from a second oxygen and put it on here like this. Now the 2 oxygens that have double bonds on them have charges that are 0. The 2 oxygens that have single bonds and 3 lone pairs, those of course still have the -1 charge. But what's the charge on our sulfur now? The charge on our sulfur, sulfur has 6 valence electrons, subtract 6 sticks and 0 dots, gives us a charge of 0. And so this is a better Lewis structure than the one that I had drawn before because we've minimized formal charges. And so this is the Lewis structure that we're going to go with. Now let's analyze it in terms of regions of electron density. And you can see that we have 4 regions of electron density. So how are they going to distance themselves as much as possible? They are going to adopt a tetrahedral molecular geometry because the sulfur has no lone pairs. It only has bonds to atoms. We could even draw out that molecular geometry. Maybe it'd be easier if I put the double bonds in the plane of the page, or the screen, I should say, like this, and I'll put a dash to the oxygen that's going in the back, like this, and I'll put a wedge to the oxygen that's coming out in the front with a negative charge like that. And so the molecular geometry, or the shape of the sulfate anion, is tetrahedral. Question 19. More molecular geometry, right? You can see that we're really hung up on molecular geometry on this exam. It says, which of the following triatomic species is linear? And so we're going to be looking at molecular geometry for all of these molecules. Let's start with the first one, SO2. Sulfur has 6 valence electrons, as does oxygen, because both of those atoms are found in group 6A. So 6 times 3 gives us 18, a total of 18 valence electrons. I'm going to start by putting double bonds on my oxygens like this because I know sulfur is going to be the central atom, as we discussed in the last problem, because it's less electronegative than oxygen. And oxygen always has to have 2 bonds and 2 lone pairs. Now, the way that it's written, have I used up all 18 electrons? The answer is no. So far, I've only used up 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2, which gives me 16 electrons that have used up. Where would I put those last 2 electrons? Could anybody help me out with that? And it's not a trick question.
On the sulfur?
Absolutely. They're going to go on the sulfur. They're going to go on the central atom. Now, if we analyze this Lewis structure, it's perfect. Both of the oxygens have a formal charge of 0. My sulfur has 6 valence electrons. Subtract 4 sticks and 2 dots equals 0. So my sulfur has a formal charge of 0. And since I have 3 regions of electron density, my molecular geometry is going to be bent because the double bonds and the lone pair are going to try to distance themselves as far away from each other as possible. And so my molecular geometry here is bent. Let's move on to the next one. This is a nitrite anion. How many total valence electrons do we have in the nitrite? Well, we've got 5 from the nitrogen. We've got a total of 12 from the 2 oxygens. So 5 plus 12 gives us 17. We have a -1 charge. We've got a total of 18 valence electrons, like that. I'm going to put my nitrogen in the middle because it's the less electronegative element. Remember that nitrogen likes to have 3 bonds and 1 lone pair, so I'm going to start like that. Now, since we've only got 2 other atoms, I'm going to have a double bond to one of them and a single bond to one of them. And I'm going to put my lone pair like this. Now, how many electrons have I used up? 1, 2, 3, 4, 5, 6, 7, 8. I know I've got to have a lone pair on this oxygen to give it a formal charge of 0. And if I put the remaining 6 electrons over here and calculate the formal charge of this oxygen, oxygen has 6 valence electrons, subtract 6 dots and 1 stick, that gives me a charge of -1. And so I can see that the formal charge on my oxygen is -1. And that's good because, let me fix this lone pair, make it a little prettier. That's good because oxygen is more electronegative than nitrogen. Now let's analyze the regions of electron density. We have 3 regions of electron density. So we'll put the lone pair up here. We'll put this single bond over here. We'll put this double bond here. And again, I have a bent geometry like that. Let's take a look at I3 with a -1 charge. Iodine, group 7A. So we have 3 times 7, that gives us 21, and then we add 1 for the negative charge, that gives us a total of 22 valence electrons. Okay, let's start by putting an iodine in the center, of course. I'm going to draw a line to each of the iodines. Remember that most of the time, elements that are in group 7A, not always, but a lot of the time, like to have 1 bond and 3 lone pairs. So if I take those 2 atoms that are on the end, give them 1 bond and 3 lone pairs, now I've used up a total of 16 electrons. 22 minus 16 gives me what? It gives me 6. Where can I put those last 6 electrons? The answer is the only place I could put them would be on the iodine. 1, 2, 3, 4, 5, 6, like that. Now let's tally up the formal charge. I know that the formal charge on these 2 iodines is 0. What about the iodine in the center? Iodine has 7 valence electrons. Subtract 2 sticks and 6 dots. So that's 7 minus 2, which would be 5. 5 minus 6 gives you -1. And therefore, that iodine is going to have a minus charge on it. I've got 5 regions of electron density, and so my electron geometry would be trigonal bipyramidal, but I've only got 2 bonds, right? Remember, molecular geometry considers what? It considers bonds, okay? We're only looking at bonds, not lone pairs. And so if I look at the bonds here, I can see that I have a linear geometry, okay? There we go. Water, I'm not going to go over water in detail because I feel like water we looked at quite a bit already in class. And I'll help you out with the molecular geometry of water. This is the Lewis structure, or sorry, the Vesper model Lewis structure of water, and it has a bent molecular geometry. And the last one, which is germanium dichloride. Well, we've got germanium, which is in group 4A, so it's got a total of 4 valence electrons plus 14 from the chlorines. That gives me a total of 18 valence electrons. I'll put my germanium in the center, put my 2 chlorines. Again, the halogens usually have 1 bond and 3 lone pairs. That gives me 8 times 2, which is 16 electrons used. I got 2 left. I'll put them on the germanium like that. Now we've got 3 regions of electron density. The formal charge of my germanium is 0. The formal charge of my chlorines is 0. Everything's perfect. And so when I draw the molecular geometry correctly, since I've got 3 regions of electron density, the electron geometry will be trigonal planar, but the molecular geometry will be bent. Again, a lot of bent molecules here, huh? Except for I3 minus, which was linear. All right, question 19. That's a wrap for that one. You can see how scratch paper is going to be beneficial during this exam. We don't expect you to, do these things on the back of your hand. It's always handy to have a good piece of scratch paper or 3. Okay, question 20. Which of the following species is square planar? And if you're wondering, they must expect me to be able to draw these Lewis structures in a reasonable amount of time in order to determine the molecular geometry. And the answer is yeah, absolutely. Absolutely we do. Now I'm going to go over this one a little bit quicker than the last ones because I spent a lot of time tallying up valence electrons. I expect you to know how to do that by now. Let's start with selenium tetrafluoride. Selenium is in group 6A. It's got a total of 6 valence electrons. I have 6 plus 28. That gives me 34 valence electrons. When you draw the Lewis structure, you find that you have 5 regions of electron density. And so it's going to adopt a trigonal bipyramidal electron geometry. But one of the regions of electron density is a lone pair. And when you have a trigonal bipyramid and you remove one of the atoms and replace it with a lone pair, it adopts this shape, which is called the seesaw shape. Okay, I distinctly remember my model of the seesaw that I showed you guys in lecture one day. Anyhow, the next one is xenon tetrafluoride. Xenon is a noble gas. It's got 8 valence electrons. 8 plus 28. That means I've got 36 valence electrons. If we draw this one over here, you can see from the Lewis structure that it's going to have 4 bonds to fluorine and 2 lone pairs. So that would give me something that looks like this. Remember, fluorine never breaks this rule. Fluorine always has 1 bond and 3 lone pairs. So you can hang your hat on that rule. Mr. Deon is saying right now that there's no exceptions to that. And when you draw the molecular geometry, you see that you end up with something that is square planar. Okay? So that must be our answer. I'm not even paying attention to the answer. I'm having so much fun drawing Lewis structures and molecular geometries. Okay, so that's the answer. It's xenon tetrafluoride. You know what? I don't like questions that the answer is right away. I like to dig around a little bit. Let's try the next one. It's carbon tetrachloride. We got 28 valence electrons from the 4 chlorines plus 4 from the carbon. That gives us a total of 32 electrons. Well, this one, I don't like to use the word easy and chemistry in the same sentence, but remember that carbon always has 4 bonds, okay? And like this, and the halogens usually have 1 bond and 3 lone pairs. So we could just put all of our chlorines on the end like this and like so, and we end up with a tetrahedral molecular geometry, tetrahedral, like that. Next one is the phosphorus tetrabromide cation. Phosphorus has 5 valence electrons. We've got 28 from 5 and 28 is 33. We subtract 1 because we've got a positive 1 charge, so we've got a total of 32 valence electrons here. Now, when I draw the molecular geometry or the Lewis structure for this, I find that phosphorus will have 4 regions of electron density. So it will look like this. Okay, and each one of them will be a bond to the bromine like this. Now remember, bromine is a halogen, so it's comfortable with 1 bond and 3 lone pairs. But phosphorus is in group 5A. And overall, we're supposed to have a positive 1 charge. What's the formal charge of this phosphorus? 5 valence electrons subtract 4 sticks and 0 dots gives you +1. And therefore, the charge on that phosphorus is +1. And there's our Lewis structure. So our molecular geometry here is tetrahedral. And then the last one, which is, I've got bismuth, the bismuth tetraiodate ion, so BiI4 with a -1 charge. Here I've already tallied up the electrons. I've got 34 electrons. And you find that you have 5 regions of electron density around the bismuth, and one of them will be a lone pair. And so we're going to have that same old, oh, good gravy, Mr. Deon. There we go. Draw a dash, draw a wedge, like that. Remember that when you have the trigonal bipyramid, when you start removing atoms and replacing them with the lone pair, you start with the equatorial positions first, right? These 3 positions, these are equatorial. These ones here, these are axial. So again, always start with the equatorial, and we end up with the seesaw. There we go, seesaw. Okay, there you go. Question 20. Let's move on to question 21. Which of the following species is trigonal pyramidal? They don't stop, do they? They don't stop. Okay. Let's start with this one here. Bromine trifluoride. Both of these elements, bromine and fluorine, are halogens. They're both found in group 7A. That means that they both have 7 valence electrons. 7 times a total of 4 atoms that all have 7 valence electrons. So 7 times 4 gives me 28 valence electrons, like that. If we remember that bromine is going to be the central atom because fluorine is more electronegative, we've got 3 fluorines like that. Remember, fluorine can only ever have 1 bond and 3 lone pairs. Now I've used up 8 times 3, which is 24 valence electrons. I've got 4 left. They're both going to go on the bromine. Now I've got 5 regions of electron density. And so when I have 5 regions of electron density and 2 lone pairs, I'm going to have a molecular geometry that looks like this. Can anybody name this molecular geometry while I wrap up drawing it? I don't know if we've seen this one this morning. Can anybody name that molecular geometry?
Trigonal bipyramidal.
That would be the electron geometry. I'm talking about the molecular geometry. Remember, molecular geometry only considers the bonds. And I see that some people have put in the chat T-shaped. Yeah, so this molecular geometry is T-shaped. Kind of looks like the letter T. The next one, we have arsenic trihydride, ASH3. Arsenic is in group 5A, so it has 5 valence electrons, 5 plus 3, so we have a total of 8 valence electrons. Remember, hydrogens, again, I don't like to use the word easy in chemistry class, but hydrogen can only ever have 1 bond. So that tells us that our arsenic must have 3 single bonds to hydrogen like this. We've got 2 electrons left over. They're going to go in the arsenic like this. So the arsenic trihydride has 4 regions of electron density, one of them being a lone pair. And we'll put a hydrogen here. We'll put another hydrogen in the back, and we'll put another one in front like that. And so you can see that the electron geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. Okay, pyramidal. And so that's our answer. That's our answer right there. I'm going to go over the next ones kind of quickly. I keep saying that and then I keep talking, but DF3, so boron trifluoride. The molecular geometry for boron trifluoride, remember that boron can be electron deficient. It doesn't need to have an octet of electrons. Okay, this is a trigonal planar molecular geometry. Boron trichloride is in the exact same vein. It's going to be a boron with 3 chlorines. Pardon my handwriting. So it's also trigonal planar. And the last one is Dilithium 3 with a 2- charge. Let me get a different color here. Dilithium is in group 6A, So we have 6 times 3, which is 18, plus 2 for the 2 minus charge. That means we have a total of 20 valence electrons. We'll start with the tellurium like this, okay? And we'll put bonds to the other telluriums like that. And if you fill up the octets of the outer ones, they're both going to have a -1 charge. And now I've used up 8 times 2, which is 16. I've got 17, 18, 19, 20. There we go. The 2 telluriums on the ends have a -1 charge, and that gives us a total of a -2 charge. And so the molecular geometry here, because we've got 4 regions of electron density, but 2 bonds, here it would be bent. I'm not going to draw the bent shape for you, but you should know by now how to draw a bent shape. Okay, question 22. Which of the following species can form geometric isomers? Which ones can form geometric isomers? Well, let's take a look at these compounds and see if we can figure out, when we can make geometric isomers. So geometric isomers are isomers that have the same connectivity. The atoms are connected the same way, but they can't be superimposed one upon the other. Okay, they're going to be different molecules. Okay, they're going to have different physical properties because they'll have a different dipole. And let me try to explain this one to you the best I can. I'll tell you right away that the answer is this one here, SF4Cl2. Let me exemplify why the first one doesn't have geometric isomers. So we'll start with germanium tetraiodide. Germanium is in group 4A. It's got 4 valence electrons, plus I've got 4 iodines. They each have 7 valence electrons. That's 28 plus 4. That gives me 32 valence electrons, like this. If I put my germanium like this, and I'm going to have 4 regions of electron density, like this. Okay, if I swap out any of these iodines, if I switch them around, am I ever going to end up with a different compound? The answer is no. Let's say I swapped, let's say I switched the position of these 2 atoms. Am I going to have a different compound? The answer is absolutely not. I won't. And so I will not have geometric isomers, or GeI4. Okay, let's look at SF4Cl2. Now in SF4Cl2, I have a total of 7 times 6 from my halogen. 7 times 6 gives me 42, plus 6 electrons from the sulfur. So I have a total of 48 valence electrons. Sulfur is going to be my central atom, and it's going to have 6 regions of electron density. And so it's going to adopt a octahedral molecular geometry. Now I'm going to take this and I'm going to copy it. Copy. I'm going to paste it over here. Okay, and I'm going to move this guy out of the way for him to work. Now let me show you what I mean by geometric isomers. If I take those 4 fluorines, okay, let me maybe write the fluorines in a different color. If I put the 4 fluorines here so that the 4 fluorines are, square planar with respect to each other. Of course, there's nothing here that's square planar because there's 6 atoms total. But if I put the 4 fluorines like this and the 2 chlorines, one up and one down like this, okay? That's one way that I could arrange those atoms, okay? That's one possibility. What if I swapped this fluorine with this chlorine? What if I switched their positions, okay? Let's give that a try. So what if I put a chlorine here and a chlorine here, like that, okay? And then I put my fluorines back in like this. And like that. If we look at the first structure that I've drawn, who could tell me what the angle is between the 2 chlorines? What's the angle just between the 2 chlorines? It's 180 degrees. Exactly. Thanks, Ashlyn. Right? This angle here is 180 degrees. What's the angle between these two chlorines over here? You can tell me what the angle is between those two chlorines. And it's not a trick question. It's 90 degrees. Exactly. This is a 90-degree angle. Okay? And so these are clearly two different molecules. Remember, the sulfur is still connected to 4 fluorines and 2 chlorines in both of them, but they are different molecules. Let me prove it to you again. If I delete all of this, black ink that I put on here carefully, let me show you something else. What if I picked up one of these molecules and tried to plop it on top of the other? Okay? If I take this guy and I pick it up and I try to plop it on top, you can see that the chlorine and the fluorine don't match, right? Can everybody see my animation? I'm really trying here to show you that they don't fit on top of each other, okay? And if you're thinking, oh, Mr. Deon, it's because you don't have them oriented in the right way. If you spun the other one around, it's gonna fit on top of it. The answer is no, it won't. Absolutely, it won't. Okay? You might have to make a model to prove that to you. And this is one of those questions that shows or demonstrates why models are so great in chemistry. They're really, really helpful for this kind of thing. If you have a difficult time visualizing something that's in 2D and then putting it in 3D in your mind, models can help a lot. And so that's the answer, is that it's SF4Cl2. It has 2 geometric isomers. Okay, I didn't mean to do that. I wanted to move them out of the way. There we go. Now somebody's asking me about CH2F2. And the answer is it can't be CH2F2, and I'll show you why. If we look at xenon difluoride, so we could even look at xenon difluoride quickly. So if you draw the molecular geometry of xenon difluoride, it's going to be linear, and there's no way that you could rearrange those fluorines to get a different molecule, okay, like that. But if you look at the next one, CH2F2, it's going to have a molecular geometry that looks like this. So it'll have, 4 regions of electron density, because hydrogen and fluorine can both only ever have one bond, except fluorine has one bond and lone pairs. Hydrogen does obviously not have any lone pairs. Okay? There is no way that I could switch those. Okay? If I number these atoms, 1, 2, 3, and 4, you tell me which ones that I could swap to make 2 different molecules, and I'll give it a shot. If anybody dares, and I'm just teasing, but just tell me which atoms to swap and I'll do it. And then we'll see if we have 2 different molecules. Switch 2 and 3. Okay, let me make a model here for you. So, building the model as we speak here down in my basement. Okay. So if I switch 2 and 3, so I'll have this one like this, and then if I switch 2 and 3, it'll look like this. Okay. I'm going to do this, but with models. So let me get my camera here for you. Okay, so here are 2 models of CH2F2. Okay, and I tried to swap those atoms the way that students asked me to do it. No matter what I do, these 2 molecules will always be identical. Okay, if I take this one and I put it like this, like that, you can see how everything overlaps. The whites overlap, the greens overlap, and these greens overlap. Okay, there's nothing I can do. I can swap any 2 you want. Swap these. Okay, I could swap this and this. It doesn't matter. Whatever I do, I could put this in a blender. Okay, I'm always going to end up with this. Always going to end up with 2 molecules that are identical. Okay, for that example. So those cannot be geometric isomers. Does that help a little bit? Okay, great. Yeah, it's not a simple concept. In fact, it's one of the trickiest things about Lewis structures and molecular geometry is that it's very challenging to manipulate something that's in 2 dimensions, right, on a screen, and manipulate that in your mind. Not trivial at all. Don't ever think that Mr. Deon's standing here going, oh, that's easy. No, it's not. It's very difficult. It's more difficult for some people than others, but it's something that can be learned. I think it's something that can be learned. I'm just going to show you chlorine trifluoride quickly. Chlorine trifluoride has 5 regions of electron density, but it only has 3 bonds to fluorine. So if I draw my chlorine, I have a fluorine here, and a fluorine here. And so it's going to have a T shape like this, but there's no, oops, I meant to draw a lone pair there, didn't I? There we go. So I have a lone pair here, and then I have another lone pair coming out of the page like this. There's no way that I can swap any of these fluorines and end up with a molecule. If I swap any of them at all, I'm going to end up with the same molecule. All right, so geometric isomers. Okay, geometric isomers. And just to put this bug in your ear, and I'm kind of just yammering on about the same problem over and over, but I think it's worth it. Where we saw geometric isomers in class was when we looked at the molecule CH2, C2, it was C2H2, so it was this. We had something that looked like this, where we had, you know, a fluorine like this, and a fluorine like that, and a hydrogen like this, and a hydrogen like this. So this is C2H2F2, okay? Now, that's one Lewis structure for C2H2F2, and I'm not talking about this question anymore, I'm talking about something different. If I make this compound, where I have the 2 fluorines on the opposite sides, like this, my question to you is, are these the same compound? Are these the same? Yeah, the answer is no, okay? And the reason why these are not the same compound, I covered it in last class, but I'll remind you, it's we don't have free rotation around a pi bond. We can't rotate a pi bond. And so if I try to take this molecule, okay, and I try to overlap it on top of this one, you can't do it. So these are, in fact, these are geometric isomers. Now, I don't think this is covered in our slides or in our textbook, but when the 2 fluorines are on the same side of the molecule, we call this a cis arrangement, and when they're on opposite sides of the molecule, we call that a trans arrangement, so cis and trans. Okay. Somebody has their microphone on. I can't tell who it is because it's not, the person isn't being very loud, but if you could all check, because I keep hearing clicking sounds, appreciate it. Okay, question 23. Which of the following molecular geometries will always form molecules that have dipole moments provided that the central atom has an electronegativity value that's different from the outer atoms? Well, octahedral won't, right? Because if I have a central atom and I have atoms at all 6 of the points, okay? There we go, something like this and something like this, okay? The octahedron, if I did have, you know, dipoles in each one of these bonds, they're all going to cancel each other out, okay? So no for the octahedron. If I draw a tetrahedron, okay, the answer is no, again, for the same reason, because all 4 points of the tetrahedron are equally distant from each other, and they're all pulling in equal and opposite directions. They're going to cancel, and so there will not be a dipole moment there. Let's look at the trigonal planar. The trigonal planar arrangement looks like this, and the answer is no for this, because even if I did have 1, 2, 3 dipoles, they're pulling in equal and opposite directions, and so they would cancel out. So the answer is no. The next one is square planar. So I'll use the red pen for square planar. So square planar would look like this. If I would have A, I would have 4 x's like this. And again, those are pointing, the dipoles would be, you know, if x is more electronegative, the dipoles would all be pulling to the sides of a square. And so the answer is no for that. But if I look at bent, okay, if I have a bent molecular geometry, I'm going to have my central atom, and then I'm going to have the two X's going down like this. Now, it wouldn't matter if the bent came from whatever molecular geometry, okay? Let's just imagine it came from a tetrahedron, okay? For example, okay, it could come from a trigonal planar molecular geometry, so on and so forth. But again, these dipoles are both pulling down like this, so the resultant dipole is going to be pulling down like that. So when I have a bent molecular geometry, I'm going to have a net dipole. And so the answer is bent will always have a dipole moment when you have central atom that has different electronegativity values than the outer atoms. Number 24, which one of the following choices provides the most complete description of a pi-type orbital? Remember that when we made sigma bonds, right, when we had sigma bonds, this was the result of side-to-side overlap of s orbitals, or not even a side, it's just s orbitals overlapping. Or it's when we had head-to-head or end-to-end overlap of p orbitals. So we have one like this and one like this. These are p orbitals. Of course, I don't want to forget my electrons that are shared. Okay, that's how we form sigma bonds. But pi bonds are always formed from the side-to-side overlap of p orbitals. So we have one p orbital like this, and Lord help me. Okay, we have another p orbital like this. Oh, good gravy. Anyhow, and they're overlapping side by side. That's not very good, is it? Anyhow, and then they have two electrons that are shared like that. Give me a thumbs up if you at least follow my drawing a little bit. Mr. Deon is not much of an artiste this morning, is he? Anyhow, a pi bond is formed by side-to-side overlap of p orbitals. And so if you look at all these, the first one, it says an orbital in which the electron charge is concentrated on the far side of the nuclei. Well, that's not true because the electrons are going to be equally distributed throughout the bond, or sorry, they're going to be more between the nuclei rather. What else? An orbital with an electron charge that is concentrated between the nuclei. An orbital in which there are no electrons. An orbital that is a cross section along the internuclear reaction, similar to a p orbital, and concentrates the electron charge between the nuclei. So this is the best answer, right? Because when you get that whole thing together, okay, it actually, now again, forgive me, this isn't going to be good, but it looks, maybe something more kind of like this, where you have the p orbital where they overlap, kind of like that. Anyhow, that's my best I can do on a Friday. Okay, Friday. That's not an excuse, is it? Monday is supposed to be the hard morning, isn't it? Anyhow, so this is the best answer, is the one that I have highlighted in yellow. Okay, let's move on to 25. What's the electron configuration of a molecule? The Be2 molecule, right? Diverillium. And, we looked at electron configurations for molecules in the last part of chapter 11. Remember, I prepared a YouTube video that covers that in gross and dirty detail. And if you have to refer to the molecular orbital diagram for molecules, feel free to do that, to look at the MO diagram that's provided on the handout for practice, for exam 2 and practice exam 2. Now in diverillium, beryllium has a total of 2 valence electrons. It has a total of 4 electrons overall, though, and we want the entire electron configuration. So we're going to consider all of the electrons. Now, again, one beryllium atom has 4. So let's write that down. Beryllium is element number 4. Okay, therefore, it has 4 electrons. So if we take 4 electrons times 2 for the 2 berylliums, that gives us a total of 8 electrons. Now, I'm not going to refer over to I'm not going to project the MO diagram, but I'll just help you out with it. We know that we start with a sigma 1s orbital, and then we have a sigma star 1s orbital, right? And those come from the bonding orbitals formed from overlap of 1s orbitals. Maybe I should have drawn this out ahead of time, right? Anyhow, then I have a sigma 2s, and I have a sigma star 2s. Okay, like this. Go. And if you're like, why are you drawing all this out, Mr. Deon? I do it because I find it helpful. I find it very helpful in coming up with my electron configuration. Now, if I have a total of 8 electrons, I'm going to start filling up my orbitals. 1, 2, 3, 4, 5, 6, 7, 8, like that. So there's all of my electrons. Now, if I just start from the bottom in terms of energy, and I go up to higher energy, what have I got? I've got a sigma 1s. I've got 2 electrons in that. I've got a sigma star 1s. I've got 2 electrons in that. I've got a sigma 2s, and I've got 2 electrons in that. Oops. Oh. And then I've got a sigma star 2s, and I've got 2 electrons in that. And if I look at all these answers, the one that matches up with that is this one right here. So electron configuration for a molecule. Again, I highly recommend watching the video that I put together about that. It covers the subject in dirty detail. All you have to do is know how to fill up the molecular orbital diagram to write out the electron configuration of a molecule. The next one is kind of an interesting question. I would call this question a conceptual question, because if you think about diatomic molecules, they have 2 different atoms in them. The only one that I covered in the slide or the video that I put together about section 11.3, chapter 11.3, whatever you want to call it, the only one that I covered in my video, if you look at it, is NO. Okay, was NO. Now, if we look at the total number of valence electrons, right, for each one of these species, there's something interesting that you'll notice about them really quickly, because we're looking for something that's going to be diamagnetic. Now, when something is diamagnetic, that means that what? It's not going to be attracted to a magnet, so not attracted to magnet. That's the first thing. But why is it not attracted to a magnet? The reason why is because all electrons are paired. Okay, now if all of the electrons are paired, the only way that you could have all of the electrons paired together is if you had even number of electrons. It's the only possible way that could happen, right? So if we look at boron and carbon together in a molecule, boron has 3 valence electrons plus 4 from carbon, right? That gives you a total of 7 valence electrons. So there's no way that could be diamagnetic. If we look at lithium and beryllium bound together, lithium has a total of 1 valence electron, and beryllium has 2. That gives me 3. That's an odd number of valence electrons, so there's no way that could be diamagnetic. We go to the next one. We have oxygen and fluorine. Oxygen has 6 valence electrons. Fluorine has 7 valence electrons. That gives us 13 valence electrons. Again, cannot be diamagnetic. There's no way we can have an unpaired electron. We look at carbon and nitrogen bound together. Carbon has 4 valence electrons plus 5 from nitrogen. That gives us 9 valence electrons. Again, we're still not there. Okay, all of these have, what do they all have in common? They all have odd numbers of valence electrons. Therefore, cannot be diamagnetic. Not digmagnetic, diamagnetic. Like that. Okay, but if we look at the last one, we have a carbon and an oxygen. Carbon has 4 valence electrons, and oxygen has 6 valence electrons, which gives us a total of 10 valence electrons. That means it's the only possibility, because only when we have an even number of electrons could all of the electrons be paired up. And so the answer is carbon monoxide is the only species that is expected to be diamagnetic out of this series. Now, let's do a problem where we have to refer to molecular orbital diagrams. So I'm going to solve this problem using molecular orbital diagrams. So I'm going to have to switch files here just for a second. Now, remember, you're going to be given the molecular orbital diagrams. Let me just write them down on a piece of paper because I don't have them in order in my notes. So C2+, then we have Be2+, then we have N2, then we have B2-, and then we have Li2. The question simply asks us, which one of the following species has the longest bond length? Now, who could tell me what the relationship is between bond order and bond length? Okay. If I have a long bond length, am I going to have a low bond order or a high bond order? What am I looking for here? The lowest or the highest bond order? Exactly. If I want to have the longest bond, if I'm looking for the longest bond, I'm going to have the lowest bond order. So that's what I'm looking for. I'm looking for the bond order of all 5 of these, and I'm going to figure out which one has the lowest bond order, because we know as bond order decreases, right, then bond length is going to increase like that. Okay, now I'm going to switch over to the molecular orbital diagrams. And again, you're going to have this at your disposal. And we'll start by looking at C2 plus, so C2 plus, like that. Carbon has 4 valence electrons. 4 times 2 is 8. We've got a +1 charge. That means we've got a total of 7 valence electrons. Let's start filling up the orbitals. 1, 2, 3, 4, 5, 6. Remember Hunt's rule, the bus rule? Okay. Remember, we can't go 5, 6 like this. We have to go 5, 6, 7. Now, bond order is equal to the number of electrons in bonding orbitals, subtract anti-bonding orbitals, multiplied by a half. Okay. I kind of use the same abbreviation twice here. I use bond order and bonding orbital. I use BO for both of them. Anyhow, hopefully follow me on that. Now, in bonding orbitals, how many do I have in bonding orbitals? I've got 1, 2, 3, 4, 5. So that gives me a total of 5. How many do I have in anti-bonding orbitals? Anything with a star by it is an anti-bonding orbital. So I've got 5 minus 2. 5 minus 2 is 3. I multiply that by a half, and I get 1.5. So that's the bond order for C2 plus. Okay, so now I've got C2 plus. I'm going to write it down here. It's 1.5. Next, we're going to look at diverillium. I put a lot of these in this file, so I'd have lots of room. So I've got diverillium with a positive charge. So I've got Be2 plus. Beryllium has 2 valence electrons. 2 times 2 is 4. I would subtract 1 for the +1 charge. So I've got 1, 2, 3 electrons. My bond order is going to be equal to 2 electrons in the bonding orbital. Subtract 1 in the 1 anti-bonding orbital, multiplied by a half. 2 minus 1 is 1. Multiplied by a half is 0.5. So we have 0.5 for Be2 plus. Let's keep moving. Let's do the next one, which was what? Nitrogen, N2. Okay. Remember, the diagram that I'm using is the one that considers orbital mixing. And so I used this one here, right, from dilithium to dinitrogen. That's it. Where was I? So for N2, I've got a total of 10 valence electrons. Let's start filling up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My bond order is going to be equal to, how many do I have in bonding orbitals? I've got 1, 2, 3, 4, 5. So I've got 5 minus 1, 2. What am I doing wrong here? Sorry, I missed 2, didn't I? I've got a total of 8. Good gravy, Mr. Deon. You need to practice your counting. I've got a total of 8 in bonding orbitals. Didn't mean to do that, and I bet you everything I just wrote is deleted. Yep. Okay, let's start over. Okay, where was I? N2 is a total of 10 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My bond order is going to be equal to 8 in bonding orbital. Subtract 2, multiplied by a half. So that gives me a bond order of 3 for nitrogen. Let's keep going. The next one is B2 with a -1 charge. Now I have B2 with a -1 charge. Boron has 3 valence electrons. 3 times 2 is 6. I add 1 for the -1 charge. That gives me 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. My bond order is going to be equal to 5 minus 2 multiplied by a half. That gives me 1.5 again. And then I'm going to do the last one, which is dilithium. So for dilithium, Li2, lithium has 1 valence electron. So that means I've got a total of 2 valence electrons, 1, 2. My bond order is going to be equal to 2 minus 0 multiplied by a half, which gives me a bond order of 1 for my dilithium. Now I've calculated all the bond orders. I go back here to my practice exam. I have to go somewhere down here, okay? And now I'll write down all those bond orders. Or let me just move this out of the way. That, okay. For C2 plus, it was 1.5. For diverillium with a +1 charge, it's 0.5. That's obviously the answer. It's the lowest bond order. The next one was 3. The next one was 1.5. And the last one was 1, like that. And so just by calculating the bond order, again, the lower the bond order, the longer the bond length. And we finished that one. Where are we? Question 28. Got time. Got 3 questions left. How many valence electrons are there in I3 minus anion? Hopefully you can do this one kind of like half sleeping, you know, and I'm kind of being facetious here, but I would expect you to be able to calculate this one pretty quickly. Right? Iodine is in group 7A. Okay, I is in group 7A. That means it's got 7 valence electrons, right? 7 valence electrons. So if I have 7 valence electrons times 3 in my I3, that equals 21 electrons, but I've got a -1 charge, so I have to add an electron, and that gives me a total of 22 valence electrons. So the answer is 22. Question number 29. If you're unsure how to solve this problem, I can show you how to do it really quickly. It says methyl ethyl ketone, abbreviated MEK, is a common anti-knock agent that's added to gasoline. How many sigma bonds and how many pi bonds are there in methyl ethyl ketone in this molecule depicted below? While you're thinking about it, I'm going to rewrite the molecule a little bit bigger here. And one thing I've noticed about this is they've used what's called a bond line structure, which leaves out carbons, which you guys are not used to. So I'll help you out by drawing this out. And if you're wondering, you know, are you going to leave carbons out on the actual exam? The answer is no. You know, I didn't write this question, of course. Somebody else did, right? Okay. Anyhow, when you all take organic chemistry with me, you'll learn how to remove carbons from structure. So remember, the first bond between 2 atoms is always a sigma bond, right? Right, Blake? Right, the first bond is always a sigma bond. So if I use yellow, if I have my sigmas in yellow, this is a sigma, 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 sigma. So anytime you just have one bond between 2 atoms, it, my friend, is a sigma bond. Now remember, I said the first bond is always a sigma bond. You see there's a double bond to the oxygen. I could either highlight that one and say it's a sigma, or I could highlight that one and say it's a sigma. I don't care. Okay, either way, one of those bonds is a sigma. Anything after a sigma is a pi bond. Anything after a sigma is a pi bond. Oops, I didn't mean to use that. I wanted to use green, like that. Okay, so this is a pi bond, like that. Anything after a sigma is a pi. So if we tally these up, right, the sigmas, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 sigmas, and we've only got 1 measly pi. So 12 sigma bonds and 1 pi bond, and so our answer is right here. Give me a thumbs up if you follow me on that. You think you could nail that one? If you had the carbons drawn in, and again, I wouldn't leave those out on the actual exam. All right, wonderful, wonderful. Happy to hear it. Great. Let's tackle the last question. Question 30. This is kind of a conceptual question, I think. And it just asks us about this molecule, C2H4. Which one of the following choices is an accurate description of the bonding and shape around each atom in C2H4? Well, in C2H4, I've got 4 valence electrons from each carbon, and there's 2 of those, so 4 times 2. And I've got 1 valence electron per hydrogen, and I've got 4 of those. So that gives me a total of 12 valence electrons. If I start trying to piece this guy together, if I start trying to put this molecule together. What do I know about carbon? Right, carbon always has 4 bonds when it's neutral. Hydrogen always has 1 bond. Okay, so that tells me that I've got to have something like this, where I have the carbons bound to each other, and I'm going to have my hydrogens like this. Now, so far I've used up a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. I've got 2 left over. If I put them on this carbon like this, there's an issue. Because this carbon does have a complete octet, but its formal charge is 4 minus 3 sticks and 2 dots, which gives it a charge of -1. So we'd have to put a minus here. The other carbon has a formal charge of 4 valence electrons minus 3 sticks and 0 dots, which would be +1. That would give me a positive charge here. Okay, now you might be thinking, hey, Mr. Deon, +1 and -1, that gives me 0. It's all balanced out. There's a big problem, though. The carbon on the left has an octet, but the carbon on the right does not have an octet. So how could I fix this to make it better? Does anybody have a suggestion? Yeah, exactly. Thanks, Emma. Thanks, Sierra. Absolutely. So what my students are saying is they're saying, Mr. Deon, take that pair of electrons and make a double bond, right? And then I end up with this molecule here. This is called ethylene. Ethylene. So there we go. Now, if there's 3 regions of electron density around this carbon, right? Remember, a region of electron density is a single bond, a double bond, a triple bond, a lone pair, or an unpaired electron. I've got 2 single bonds and 1 double. That means that I have 3 regions of electron density around this carbon and 3 regions of electron density around this carbon. When I have 3 regions of electron density around a carbon, who could tell me what the hybridization will be of these carbons? We went over hybridization quite a bit in class. It's not sp3, because sp3 you'd have to have 4 regions of electron density. Yeah, it's going to be sp2. So both of these carbons, okay, both are sp2 hybridized, like that. And if you read all these answers, and I'm not going to plow through all of them because it's pretty exhaustive, but you see that in each answer, it mentions hybridization, right? We have sp3, sp, sp3d, sp3d2. So as long as you're able to figure out the hybridization of those 2 carbons, then you're going to know that the answer has to be the first one. Each carbon is sp2 hybridized, makes 1 localized sigma bond, and each hydrogen and with each hydrogen and another 120 degrees apart with neighboring carbons. The p orbital forms a double bond between the 2 neighboring carbon atoms.